Hey guys, I'm going to be talking about Wi-Fi attacks and atypical CTF challenges today. As many of you know, I am the tech lead, so this is kind of like what I do for the club most of the time. And yeah, all right. So standard CTF challenges or categories. You have PWN, web, reversing, cryptography, forensics, OSINT, and all of those. I think they're a little bit overdone. So when I make CTF challenges, generally I try and do different stuff. And whether that's my choice or it just like happens is kind of up to fate. So as RITSEC tech lead, I have to make CTF challenges out of things that shouldn't be CTF challenges, like containerization, physical security, blue teaming, hardware, wireless security. All those things, it's possible, but you're like kind of limited on the things that you can do. And yeah, but today I'll be talking about all that. It's fun. All right, so ISTS challenges. I was on the CTF for ISTS, and well, let's start off. I wanted there to be hardware and wireless challenges, and you know what that means? That means I had to make all of them. So I wanted like an entire category for hardware and wireless challenges. So I ended up making 5 of them, and they actually went pretty well. So these are the concepts for all of them. For hardware, I had a pin identification one, a hidden input sequence, a circuit diagram analysis one, and then for wireless challenges, I had spectrogram and then rogue Wi-Fi network. I'm only going to be talking about circuit diagram analysis and the rogue Wi-Fi network, just because I think those are like the 2 most interesting ones. But the other ones, all the write-ups and the source code and stuff is all on my GitHub. But boom. All right, so the first one is Gate Gambit. And that's, the GitHub link right there. Here's the circuit. So competitors were given pretty much just this circuit and like a little write-up saying that this FPGA it was used in gate design for the actual hardware. Find out the input sequence from the diagram that will make the gate open. And it was just like a bunch of switches that they had to flip up and down for ones and zeros. And the way that they did that is through this circuit. So what they're trying to do is make the output 1, and given all of those logic gates, there's only one set of inputs that is possible to make that output 1. And that's, that's it. So it's 1 0 1 1 0 0 1 1, and yeah, that's everything. This probably took competitors like a good 20 minutes to do it. Just because if you don't really know what like a NOR gate or an XNOR gate is, you can't just like do the truth table in your head. You kind of have to look it up and then transcribe everything. But this took me about 2 minutes to like finish. It's pretty shrimple. Yeah, and so this is the output. This is that's the D10 Lite FPGA that they were all given, and it came like pre-flashed. I'll talk about that in a minute, but down there on the bottom, let's get a closer look at that. That is our input sequence. So as you can see, it matches the solved circuit, 1 0 1 1 0 0 1 1. Hey, look at that. And the extra 1 at the end is key 1, which is literally just a button in the top right of the image. And the reason that I added the key, as you can see in the circuit, just like goes straight to the end, so they know it has to be 1. The reason that I made that a 1 is because I just wanted them to just input, like hold that down, and then as it was printing out the flag, they could stop it whenever they wanted. Yeah, so that's the input sequence. It's really just ASCII. So that right there, 0 1 0 1 0 1 0 0, that's the ASCII notation for the letter T, capital letter T. And so as they solve it, they hold down that button, all of the switches are flipped to how I want them to be. It'll print out the flag, just like hold for a second, then go to the next character, next character, next character, until they have the entire complete string, which would be ISTS access granted. And so if you're really interested in VHDL, as I'm sure many of you are, this is what it actually looks like. So you have your pin definitions, basically just on the left side there. That's basically just saying, hey, The clock pin, switch, button, reset, all of those are going into the device. And button 3 down to 1 just means that there's 3 buttons there. So there's 3, 2, and 1. And then Q and clock out are the outputs. So Q is a 4-bit output. Actually, this seems a little bit old. I probably could have grabbed a more updated one because it's 8 bits now. Originally was 4 bits. So that's what that Q is. And then clock out is just like a flashing light to let them know. Yeah. That but one all the way down on the end, all the way down on the left side, that will just flash on and on just to let them know that it's changing characters. And then on the right side, that's the order that they're all going to go through by nibble values. Yeah. Fun fact, a nibble's half of a byte. Isn't that fun? All right. So then signal definitions. Basically what a signal definition is it's just a wire. So that first instance is just taking switch 1 and switch 2 and XNORing it. So if we go back down to here, that is, can you see my mouse on there? Oh yeah, you can. It's this one right here. So that's the one that it's going off of. And that instance, you know, no number would be this wire right here, and that's how you can like physically define how all of this hardware and all these logic gates are connected. Yeah, so pretty cool. And then the finite state machine that's a little bit more complicated, but pretty much it's just like sequential logic in VHDL saying like, hey, if the current state is this, and we wait a certain amount of clock cycles, which is, you know, just like a certain amount of time, change to this next state. So that is how I get it to hold each one for about a second and then keep going. Yeah. Okay. So then finally, in order to finish the challenge, I'd flash the hardware, and you can just program the .pof file to the device. And what that'll do is it has the CFMO and UFM files as well, and those get flashed to onboard memory so that on startup, like as soon as you plug in the FPGA, then it'll just already have your hardware implemented instead of just the basic hardware scheme. All right, so that's the end of that one. Then my next challenge, Handshake Havoc. This one's a little bit more involved theoretically. It took me a lot less time to actually implement, but you know, takes a lot more time to actually talk about. All right, so the challenge itself. Competitors were given a packet capture. Misspelled that one. They were given a packet capture that contains a 4-way handshake, and they're told that there's a device on the network that's transmitting. So what you could do with this is, actually, I'll talk about that in a minute, but if you were to start like a packet capture on the network, this is what you would see. It's just all encrypted. You can't really do anything with it. But hey, you know that the network name is TP-Link 0E18. It's just the router name. And yeah. So a note on WPA2 encryption, that's what this router was using. That's what most routers use. And it uses AES encryption. Yeah. So AES encryption, mutual authentication, it implements a 4-way handshake. That's really the big thing that it does. So it implements the 4-way handshake so that you can authenticate users as they're connecting to your Wi-Fi network. And in order to actually view all of the traffic, you have to first break the 4-way handshake. And once you break the 4-way handshake, then you can get the actual Wi-Fi network password. And you know, that's the easiest way to break into the network and to collect the cracked handshake. Yeah, so the tool that they would use for that, since they already have the packet capture, I made it kind of easy for them, but they would just use a tool called AirCrack TAC-NG, and that's just like a dictionary attack cracking tool. You give it a word list and the handshake, or a packet capture with the handshake in it, and then it will just like run through the entire word list and try and brute force the password. And for this one, I specifically chose the I ran cat rockyou.txt and then stopped it after like half a second so that I knew it wouldn't be too far in. Because, you know, it's going to run in sequentially. It's going to try the first one all the way down to the last one for RockYou. So that's a way that you can grab one that you know isn't going to take very long to crack. Yeah. It's the same thing as all other, yeah, just like the amount of compute power that you have. That's the limiting factor, yeah. What's the limiting factor for, what was it? What's the limiting factor for Wi-Fi cracking? Yeah, and so the limiting factor for brute forcing Wi-Fi is just the same as any other password cracking, like trying to break hashes, that kind of thing. All right. Oh, man. Okay, so time to solve it. Hop on the network. You get the password. I mean, we just got the password, Sincere Dad. And we know that there's a device that's broadcasting, keyword broadcasting. So we can start Wireshark capture. You know, just hop on the network, start a Wireshark capture on your Wi-Fi network, and you can filter by an Ethernet address that's broadcasting. And we all know that the local broadcast for MAC address is just all Fs. And so create a filter for that, and boom, there you go. You can find the ARP packet. There's obviously not going to be that many things that are using broadcast. And down at the bottom, would you like that? ISTS Hertz attack. And there's the flag. So really the cool thing about this challenge is not really how to solve it, but how it's made. And my original idea for this capture the flag challenge was actually going to be a little bit more involved than this, but I'll get into that. So the first thing that I needed was a Wi-Fi dongle that's in monitor mode. Now, every Wi-Fi chip cannot just like view all of the packets on the Wi-Fi network. Because I mean, if you think about it, say you have a Wi-Fi router that's near you and some devices around you that are connected. Really all that is just like RF radiation that's being sent from your device to the router. And there's nothing saying, since it's like a physical medium and it's going all throughout the air, there's nothing saying that an attacker can't just like sit next to you and just listen to all of your traffic. That's why the four-way handshake is so important in this kind of encryption. It's to make it so that people can't just like sit next to you and be in the same room and then just sniff all your packets. Because I mean, it's realistically the same thing as just like plugging yourself into somebody else's Ethernet port. That's literally all it is. And so in order to actually do that and to do like Wi-Fi packet injection, you need a Wi-Fi dongle that's put into monitor mode. And so there's only like a few chipsets, and they're all to the right. All the ones that I could find, actually. And you need one of those specific chips to put your Wi-Fi chip into monitor mode so that you can like listen to all of the everything being broadcasted in your general vicinity. So yeah. What I use for this is AirCrack NG, the tool suite. So AirCrack NG, AirMon NG, Air Replay, AeroDump. I used all four of those tools, and most attacks, from what I've seen, those are the most used tools. But the suite does have a whole bunch of other ones that, you know, if you're interested, go and check them out. So the way that I set up this challenge is I actually set up the network in my apartment and then did like a full deauthentication attack so that I could extract that WPA or that four-way handshake. So let's start with the network topology setup. You have two devices, only one of them is on the network. The lock up there is just saying that there's no form of communication to the router because the device on the right, you know, my laptop, doesn't have the Wi-Fi password, so it can't get onto the network. So I just like made up a MAC address. Don't take it too seriously, but that MAC 10, 10, 10, 10, 10, you know, all 10s, that's supposed to be the Raspberry Pi, and as I said before, I just had it like running a script and that script was using Scapy to transmit a ARP packet with the flag in it, just like tacked on to the end of the frame. So there's an encrypted channel of communication between that router and then the MAC address or the Raspberry Pi. And one thing to keep in mind is that none of this stuff is actually connected to the internet. You can like set up a router and like a local network, and your router doesn't actually have to connect to the internet. It just needs to like be in the general vicinity, and it practically acts as a switch at that point. So Airmon NG, this is our first tool. This is, like I said, you can switch it into monitor mode, and monitor mode is like similar to a promiscuous mode if you've ever dealt with Ethernet. You can just like view all of the packets that are being sent like through your computer or just like around it. It just sniffs everything. And so you can capture all Wi-Fi traffic in your area. Just like say I was in this room and I wanted to see everything, I could just capture all of the Wi-Fi frames. And I can also, with monitor mode enabled, I can spoof Wi-Fi frames, which is what I plan on doing. And there's the syntax for it in the bottom left. So WPA2 has a vulnerability where hosts initialize their own deauthentication, which is like so silly, and it was fixed in WPA3, thank God. But one thing to keep in mind is from these statistics, they're pretty creditable. It's wiggle.net. It's like the main war driving platform for everybody. There's 1.5 billion networks that are on there, and like 2.17% of them are on WPA3, which is like terrible. That number needs to get up way higher, but companies aren't really making WPA3 routers that much. Obviously, you know, they're still sitting on WPA2 at 75%, roughly. Yeah. Okay, so Air Replay. This one is what you use to actually transmit the Wi-Fi frames. It's similar to Scapy, but it's very nice. It does a lot of things for you. Like, it wouldn't take that long to write all of this in Scapy, but this is pretty cool. It can be used to deauthenticate hosts. And so, like I just said, deauthentication is initialized by by the user, and the router doesn't really verify that deauthentication frame is coming from the same user. So if I want to just like spoof my MAC address to seem like I'm sending packets from the other, or I'm sending frames from the Raspberry Pi, I can do that. So I can just like send a frame saying, hey router, I want to deauthenticate. I don't even have to be on the network in order to do this, which is really silly. So I can just say, hey, I want to deauthenticate. And then, you know what? Guess what? The router just says, okay, I'll deauthenticate you. And it just removes the connection from the host and requires the host to re-authenticate using the Wi-Fi password. And so that's how we get our other WPA4, or our four-way handshake. And one other thing, if you got a keen eye, that one thing that you can do with this is just, instead of doing deauthentication, you can turn this into like a DDoS attack or just like a plain DOS attack, and you can just keep sending deauthentication frames, spoofing the MAC address of this host, and you can just make it so that they can't reconnect to the router, which is kind of insane. Now, while you're running the Air Replay, you're gonna have AeroDump NG open, and with AeroDump NG, you can like sniff all of the Wi-Fi packets that are being transmitted on your in your general vicinity, and so you will eventually get the four-way handshake once that host tries to reconnect or re-authenticate with the router, and yeah, that's how you get the four-way handshake. And basically, this tool, you can set it to a specific channel, or you can just like say, hey, this is like run AeroDump TAC NG on this interface that you have your monitor mode enabled Wi-Fi card on, and it'll just like flip through all 13 Wi-Fi channels and check for any ongoing connections. Okay, so I kind of just mentioned this, but WPA2 uses the same Wi-Fi password for communication to all hosts. I mean, obviously, you type in that Wi-Fi password, and for some reason, WPA2 does like some encryption with it, like some packet encryption. So depending on the modulation mode, and you can, like as an attacker, just perform this deauthentication attack and get the Wi-Fi password, and then you can decrypt all of the traffic. It's kind of crazy. And I mean, once you have the four-way handshake, like I mentioned before, you can use aircrackng, brute force it, yeah. And then your attack is complete. You can connect to the network, or you can also spoof, you can deauth that other device and then spoof your MAC address and reconnect to the network, making it so that they can't reconnect at all. And so, from that challenge, from these challenges, I had like an initial plan for some of them. Just like an example was like last year. So the hardware challenges, they required you to like flash all of the hardware yourself in Cordis, which means that all of the competitors had to install Cordis, and it ended up making it so that most people got like super discouraged from actually doing the challenges, even though they weren't even that difficult. But so the one major change that I did this year was I made it so that like all of the FPGAs were pre-flashed and people could just like grab them, plug it in, and then start trying the challenge. And I ended up getting a good, I don't know, 50% of the competition to actually complete the challenges and probably like 80% to even try them, which was pretty great. I was happy to see it. And then the wireless challenges, I originally wanted them to do like the full deauthentication attack like I just went through, which is, you know, obviously what I had to do in order to create the challenge. And I think that would have been way more interesting and more fun. But then I also run the risk of all of the competitors just like deauthenticating every host to like RIT's EDU Roam network, which I don't really want to worry about that. So then that one also requires hardware. Like I would have to give them a monitor mode enabled dongle, which would kind of be a pain. So I don't know. Maybe another CTF challenge. Maybe for demos. That would be pretty cool. But yeah. So when you're making CTF challenges, especially when you're kind of doing like uncharted territory, you have to keep a few things in mind. You have to think about the competitor, and like what they can reasonably do in the amount of time that you're giving them. I mean, CTF challenges don't last for forever. And in a competition like ISTS, you really can only expect them to spend like an hour, maybe 2 hours on your specific challenge, or else they're just like not gonna do it. So for example, like a hardware challenge, I can't make them like dump the firmware or like do like a crazy circuit challenge and then connect to all of the I/O pins and like there were some ideas that I had, but I just deemed them too difficult for the competitors to actually do. So then be mindful of the outside impact of your challenges. Don't DDoS an entire network. That would kind of be a problem. And then know what hardware is required and order in advance. For ISTS, I ordered 6 of the DE10 Lite FPGAs, and because of like ordering issues and everything, and like shipping addresses being wrong, it didn't end up coming until like 4 or 5 days before the comp, which could have been really bad if I wasn't proactive in ordering them, you know, weeks in advance. So yeah, and then also the golden rule of the competitions. Anything can be a CTF challenge if you try hard enough. And that's what I've learned as tech lead. I can make like containerization demos, even though containerization doesn't really make that sense to be demos, or like physical security, or social engineering, which is most likely coming up in a couple of weeks. So look forward to that. There will be CTF challenges. I'll figure it out. You always can. And so one final note, Always check ChatGPT for all of your challenges, because I guarantee you that that is the first thing that every competitor is going to try, even if you tell them that they can't do it. And so when you put your challenge into ChatGPT and you give it like a pretty good write-up, and then it responds to you saying a missing condition that prevents the AND 3 gate from being satisfied, if you intended the circuit to produce y = 1 under any conditions, it's not possible. That's just like beautiful. I love seeing that, especially when the challenge is in front of me working. I just love that. I love it so much. And yeah, any questions? I feel like I did pretty good on time. Yeah, what's up? How does WPA3 fix the deauth issue? WPA3 requires packet authentication for deauthentication frames, and so it requires the user to authenticate in order to send one of those. And then also the WPA3 handshake is called a Dragonfly handshake, and that's just like way better, and it's much harder to like crack, and you can't really just like brute force it like you can with the 4-way handshake. Yeah. Any other questions? Sweet. Thank you.